The Kuiper Belt sounds like a destination, a place you fly to, arrive at and explore. It is not. It is a frozen wilderness stretching billions of miles beyond Neptune, so vast that even our fastest spacecraft needed nearly a decade just to graze its inner edge. New Horizons launched in 2006 at 36,000 miles per hour, the fastest departure speed ever achieved from Earth, and it still took 9.5 years to reach Pluto. But Pluto is only the beginning. The belt extends outward for billions more miles, and some of its most important worlds orbit twice as far as Pluto wanders. The question is not how long it takes to reach the Kuiper Belt. The question is what you mean by reaching it. If you enjoy journeys that change how you see the solar system, hit that like button and subscribe. It means a lot and helps this channel keep exploring the stories that you enjoy. Now, get yourself comfortable. Let's begin. Ask someone how long it takes to reach the Kuiper Belt, and they will almost certainly picture a single journey to a single place. Maybe they imagine a spacecraft aimed at the dark edge of the solar system, crossing some invisible line and arriving. The way you arrive at a country, or a coastline, or an island at the edge of a map. You depart from one place, you travel for some amount of time, and you get there. The answer is a number. The journey has a beginning and an end. Simple. This is the first mistake, and nearly everyone makes it. The Kuiper Belt is not a coastline. It is not a border. It is not a destination you can mark with a pin and measure a straight line to. It is a region of space so enormous that calling it a belt is one of the most misleading names in all of astronomy. The word belt suggests something narrow, something contained, something you could stretch around the solar system like a ribbon. The reality is closer to a frozen ocean. A vast, donut-shaped volume of space extending billions of miles beyond Neptune, populated by hundreds of thousands of icy worlds that no human being has ever seen up close, and stretching so far outward that our fastest spacecraft would need decades to traverse it from inner edge to outer boundary. When you ask how long it takes to reach the Kuiper Belt, you are not asking about a trip to a location. You are asking about a trip into a wilderness. And the answer depends entirely on how deep into that wilderness you intend to go. Part of the confusion stems from how the Kuiper Belt is usually described. Documentaries show a tidy ring of objects orbiting beyond Neptune. Diagrams in textbooks draw a neat donut with crisp edges. The visual language suggests something orderly, contained, crossable, but those diagrams are not drawn to scale. They compress billions of miles into a few inches on a page, making the belt look like a stripe you could drive through in an afternoon. In reality, the Kuiper Belt is one of the largest structures in the entire solar system, rivaled only by the hypothetical Oort cloud and the heliosphere itself. Understanding why the travel question tricks you requires understanding what the Kuiper Belt actually is. And what it is, above all else, is enormous. It begins at the orbit of Neptune, roughly 30 astronomical units from the Sun. 1 astronomical unit equals the average distance from Earth to the Sun, approximately 93 million miles. Multiply that by 30 and you reach about 2.8 billion miles. That is where the inner edge of the belt starts. A beam of light, the fastest thing in the universe, takes roughly 4 hours to travel from the Sun to this distance. Not at some wall or gate or visible marker, but simply where Neptune traces its path through the solar system, and where the population of small, frozen objects begins to thicken. There is no sharp boundary, no sign announcing that you have entered Kuiper Belt space. The inner edge is defined by gravitational influence, not by geography. Neptune's gravity sculpts the inner boundary of the belt the way a river shapes the edge of a floodplain. Objects that wander too close to Neptune get swept up, scattered, or flung onto wildly different orbits. Objects that stay far enough away survive in relatively stable paths, circling the Sun in the cold and the dark for billions of years, undisturbed since the planets first formed. The main body of the belt extends outward from that inner edge to approximately 50 astronomical units from the Sun. That is about 4.6 billion miles. This core region, stretching from 30 to 50 astronomical units, is where the majority of known Kuiper Belt objects concentrate. They orbit within a thick, donut-shaped volume of space, following paths that range from nearly circular to moderately elongated. Most are composed of frozen volatiles, mixtures of water ice, methane ice, ammonia ice, and other compounds that have remained solid since the earliest days of the solar system. Many are coated in dark, reddish organic material called tholins, formed when ultraviolet radiation from the sun and cosmic rays bombard simple ices over billions of years, slowly building complex carbon-rich molecules on their surfaces. These objects are planetary fossils, remnants of the primordial disk of gas and dust from which the sun and planets formed roughly 4.5 billion years ago. Astronomers divide them into subcategories based on orbital behavior. The classical Kuiper Belt objects, sometimes called cubewanos after the prototype discovery, follow relatively calm orbits between about 40 and 50 astronomical units. The resonant objects, including Pluto itself, are locked into orbital patterns synchronized with Neptune, completing a specific number of orbits for every specific number Neptune completes. Pluto completes exactly 2 orbits for every 3 that Neptune makes, a gravitational dance that has kept the dwarf planet stable for billions of years, despite its orbit actually crossing Neptune's path at certain points. This resonance acts like a protective mechanism, ensuring that Pluto and Neptune never actually approach each other closely even though their orbital tracks intersect. But the Kuiper Belt does not simply stop at 50 astronomical units. Overlapping its outer edge is a second population called the scattered disk, made up of objects whose orbits carry them on long, elongated paths stretching outward to hundreds or even nearly 1,000 astronomical units from the Sun. These scattered objects were likely flung to their extreme distances by close gravitational encounters with Neptune during the chaotic early history of the solar system, when the giant planets were still migrating through the disk of debris left over from the Sun's formation. The scattered objects swing inward periodically, passing through the main belt region before retreating deep into the outer solar system on orbits that can take thousands of years to complete. The scattered disk is not a separate, neatly divided region. It overlaps with the main belt, interleaves with it, and blurs any clean outer boundary. Where the belt ends and the scattered disk begins is a matter of definition, not of physical borders. And beyond even the scattered disk lie the detached objects, bodies whose closest approaches to the Sun still leave them far outside Neptune's gravitational reach. These objects occupy orbits so remote that no known planet could have placed them there through simple gravitational scattering. Sedna is the most dramatic known example. Its closest approach to the Sun is 76 astronomical units, already well beyond the main belt. At its farthest, Sedna swings out to approximately 1,000 astronomical units, a distance so extreme that it takes roughly 11,400 years to complete a single orbit. A beam of light, travelling at 186,000 miles per second, would need nearly a full week to reach Sedna at that distance. Whatever placed Sedna on that path, whether it was a passing star during the Sun's birth cluster, the gravitational influence of a large undiscovered planet, or some process from the solar system's chaotic infancy that we still do not fully understand, it was not Neptune. Sedna exists in a kind of gravitational exile, too far from any known planet for its orbit to be explained by the interactions we observe today. The conditions at these distances are as extreme as the distances themselves. At 30 astronomical units, the inner edge of the belt, sunlight is already roughly 900 times weaker than it is on Earth. Noon on Pluto resembles deep twilight here. At 50 astronomical units, the outer edge of the main belt, sunlight drops to roughly 2,500 times dimmer than Earth's. At Eris near 96 astronomical units, sunlight is about 9,000 times weaker. The Sun from that distance would still be the brightest object in the sky, far brighter than any star, but it would appear as a brilliant point rather than a disk. You could stare at it without discomfort. Its warmth would be undetectable. Temperatures in the Kuiper Belt hover near -230 degrees Celsius, cold enough that nitrogen, methane, and carbon monoxide exist as solid ices on the surfaces of worlds. These are not just distant places, they are fundamentally alien environments, colder and darker than anything within the planetary region of the solar system. The point is this: when someone asks how long it takes to reach the Kuiper Belt, they are asking about a structure that begins roughly 3 billion miles from Earth and stretches outward for tens of billions of miles more. The answer depends entirely on where within that enormous volume you are trying to go, how fast your spacecraft can travel, and whether you plan to fly past your target or actually stop. To feel the weight of these distances, consider the inner solar system that most people are familiar with. Mercury orbits at roughly 1/3 of an astronomical unit from the Sun. Venus sits at about 7/10. Earth is at 1. Mars orbits at approximately 1.5 astronomical units. Jupiter, the largest planet in the solar system, circles at about 5.2 astronomical units. Saturn sits at roughly 9.5. Uranus orbits at about 19. Neptune, the outermost major planet, completes its circuit at approximately 30 astronomical units. The entire distance from the Sun to Neptune, spanning all 8 major planets and everything humanity has ever directly experienced in space, covers those 30 astronomical units, about 2.8 billion miles. Every mission to every planet, every robotic flyby, every orbital survey, every lander that has ever touched another world, all of it occurred within that 30 astronomical unit span. It took the Voyager 2 spacecraft 12 years to travel from Earth to Neptune, using gravity assists from Jupiter, Saturn, and Uranus along the way. Voyager 2 remains the only spacecraft ever to visit Uranus or Neptune, and that 12-year journey, the longest planetary voyage in history at the time, brought us only to the front door of the Kuiper Belt. When Voyager 2 swept past Neptune in August of 1989, it was leaving the realm of the planets and entering the belt's outer neighborhood. But Voyager 2 was never aimed at a Kuiper Belt object. It flew through the region without stopping to visit, because the belt had not even been confirmed to exist yet. The first Kuiper Belt object beyond Pluto would not be discovered for another 3 years. Now consider that the main body of the belt alone, from its inner edge at 30 astronomical units to its outer boundary near 50, spans 20 astronomical units. That is approximately 1.9 billion miles. The belt's core region is 2/3 as wide as the entire distance from the Sun to Neptune. It is not a narrow ring at the edge of the map. It is a vast structure comparable in width to the realm of the giant planets. And if you include the scattered disk and the detached objects, the full extent of Kuiper Belt-associated populations reaches from 30 astronomical units outward to several hundred, and in extreme cases like Sedna, to more than 1,000. The Kuiper Belt region, taken as a whole, dwarfs the inner solar system by an order of magnitude. This is emphatically not the asteroid belt. People sometimes assume the Kuiper Belt is a colder, more distant version of the asteroid belt between Mars and Jupiter, a sparse ring of debris that a spacecraft could zip through quickly on its way somewhere else. That assumption is deeply wrong. The asteroid belt is roughly 1 astronomical unit wide, a relatively thin band of rocky debris concentrated between about 2 and 3.5 astronomical units from the Sun. The Kuiper Belt's main body alone is 20 times wider. The asteroid belt is mostly empty space, and spacecraft like Pioneer 10, Voyager 1 and Voyager 2 all pass through it without incident and without needing to dodge a single object. The Kuiper Belt is also mostly empty space, but its total volume is thousands of times larger. Its objects are made of ice rather than rock, and its individual members include worlds large enough to qualify as dwarf planets with their own moons, atmospheres, and complex geology. The total mass of the asteroid belt is less than 4% of the Moon's mass. Pluto alone is more massive than the entire asteroid belt combined. The Kuiper Belt is a fundamentally different kind of structure, richer, more diverse, more scientifically significant, and incomparably more difficult to reach. The belt's existence was suspected long before it was confirmed. In 1943, the Irish astronomer Kenneth Edgeworth proposed that a reservoir of small icy bodies might exist beyond Neptune, remnants of the original cloud of material from which the solar system formed. He reasoned that at such great distances from the Sun, the density of the primordial disk would have been too low for the scattered material to coalesce into a full-size planet, leaving behind a population of smaller objects instead. In 1951, the Dutch-American astronomer Gerard Kuiper published a similar idea, speculating about a disk of frozen bodies beyond the outermost planet, though Kuiper believed the region might have been largely cleared out over time by gravitational perturbations. The name Kuiper Belt stuck, somewhat unfairly to Edgeworth, and for decades the idea remained purely theoretical. No telescope was powerful enough to detect the small, faint objects that the hypothesis predicted orbiting in the cold beyond Neptune. That changed in 1992, when astronomers David Jewett and Jane Liu after 5 years of painstaking searching using the University of Hawaii's 2.2-meter telescope, discovered the first confirmed Kuiper Belt object beyond Pluto. The body, catalogued as 1992 QB1, was faint and small, estimated at roughly 100 to 200 kilometers across, orbiting at approximately 44 astronomical units from the Sun. It was not spectacular to look at. In the Discovery images, it was barely more than a dim speck shifting slowly against the background stars, but its significance was enormous. For the first time, astronomers had confirmed that the space beyond Neptune was not empty. It was populated by a vast, cold reservoir of frozen remnants from the earliest era of the solar system, bodies that had been orbiting in the darkness for 4.5 billion years, largely unaltered since the planets first took shape. Pluto, long considered an oddity, a misfit planet too small and too eccentric to belong with the giants, suddenly had context. It was not an anomaly. It was the largest known member of an entire population that had been hiding in the dark all along. Since that first discovery, more than 2,000 trans-Neptunian objects have been catalogued by observers around the world. But astronomers emphasize that this represents only a tiny fraction of the estimated total population. The belt is calculated to contain hundreds of thousands of objects larger than 100 kilometers in diameter, along with potentially millions or billions of smaller bodies too faint for current telescopes to detect. Among the known objects are the dwarf planets that have become the belt's most famous residents. Pluto, the largest and most well-known, follows an orbit ranging from 29 to 49 astronomical units, taking 248 years to complete one trip around the Sun. Eris, nearly Pluto's twin in diameter, but about 27% more massive, traces a wildly elongated orbit between 38 and 98 astronomical units, with an average distance of roughly 68 astronomical units, and an orbital period of about 557 years. As of recent measurements, Eris sits near 96 astronomical units from the Sun, roughly 3 times farther away than Pluto at its closest approach. Marquet orbits at an average distance of about 46 astronomical units, completing one circuit every 305 years. Haumea circles at approximately 43 astronomical units. Each of these worlds is a distinct destination with its own orbital path, its own distance from the Sun, and its own set of requirements for any spacecraft attempting to visit. This variety is the key to understanding why the travel time question has no single answer. A mission to Pluto near perihelion, when the dwarf planet sits at roughly 30 astronomical units, is a fundamentally different proposition from a mission to Eris at its current position near 96 astronomical units. The distance to Eris is more than 3 times greater, but the differences extend far beyond raw distance. The trajectory must be calculated differently. The launch window depends on planetary alignments that recur on different schedules. The gravity assists available from Jupiter or other planets change the speed and direction of the spacecraft in ways that are unique to each target. The communication delay at Eris is roughly 3 times longer than at Pluto. At Pluto's distance, a radio signal travelling at the speed of light takes about 4.5 to 5.5 hours to reach Earth. At Eris, it takes more than 13 hours. That means every command sent to a spacecraft at Eris would require over a full day for a round-trip exchange, sending an instruction and receiving confirmation that it was carried out. Real-time control is impossible. Every maneuver, every camera pointing, every course correction must be programmed in advance and executed autonomously. The sunlight at Eris is roughly 9,000 times dimmer than what we experience on Earth, making solar panels completely useless and requiring nuclear power sources that gradually weaken over decades as their radioactive fuel decays. The scientific instruments must be designed to operate in extreme cold and near total darkness, conditions specific to each target's environment. The Kuiper Belt does not offer a universal travel time because it is not a universal destination. It is a region containing thousands of individual worlds, each demanding its own mission architecture, its own timeline, and its own engineering solutions. At speeds comparable to New Horizons, roughly 14 kilometers per second or about 31,000 miles per hour, a spacecraft would cross the inner edge of the belt at 30 astronomical units in approximately 9 to 10 years. Depending on the exact trajectory and whether a gravity assist from Jupiter is available. This is roughly what New Horizons accomplished on its way to Pluto. 10. Reaching the heart of the main belt, around 40 to 45 astronomical units, would require 12 to 14 years of flight. Reaching the outer edge of the main belt at 50 astronomical units would take approximately 15 to 16 years. Reaching Eris at its current distance near 96 astronomical units would require roughly 30 years, and reaching Sedna at perihelion, 76 astronomical units away, would take over 23 years at that speed. At aphelion, 1,000 astronomical units from the Sun, Sedna would require roughly 3 centuries of flight at New Horizons velocity, more than 3 centuries. A spacecraft launched before the American Revolution, before the United States existed, would still not have arrived. The full span of the nation's history, from its founding to the present day, would not be enough flight time to reach one object at the far edge of the Kuiper Belt's extended population, and that spacecraft would arrive at 31,000 miles per hour, too fast to stop, too fast to orbit, able to gather data for a few hours before the target shrank behind it into the dark. These are all flyby times. The spacecraft reaches its target at enormous speed, collects data during a close approach, lasting hours at most, and then continues onward into deeper space without slowing down. It does not enter orbit. It does not linger. It does not come back. The encounter is measured in hours. The journey before it is measured in decades. And after the flyby, the spacecraft keeps going, leaving the target behind forever, receding into the dark with the data it gathered in those few frantic hours of closest approach. And all of these calculations assume you know exactly where to aim. Finding a target in the Kuiper Belt is its own enormous challenge. The belt is so vast, and its objects so small and faint, that even the most powerful telescopes can detect only a fraction of the population. When the New Horizons team searched for a second flyby target beyond Pluto, they used the Hubble Space Telescope to scan a narrow corridor of sky along the spacecraft's projected path. The campaign required years of effort, extensive computational processing, and custom search algorithms. It eventually identified Arrokoth, a small contact binary, orbiting at roughly 44 astronomical units. But finding that single object among the vast emptiness of the outer belt demanded an extraordinary investment, and the team acknowledged that success was never guaranteed. The Kuiper Belt is so sparsely populated, despite its hundreds of thousands of inhabitants, that a spacecraft traveling through its densest region can fly for years without passing within telescope range of a single known body. The belt may also be even larger than these already staggering numbers suggest. In early 2024, a team of scientists published findings from New Horizons onboard Venetia Burney student dust counter. As the spacecraft approached 60 astronomical units from the Sun, it detected higher than expected levels of interplanetary dust, the tiny frozen remnants of collisions among Kuiper Belt objects. According to existing models, the dust density should have been declining at that distance, well beyond the main belt's supposed outer edge at 50 astronomical units. Instead, the readings remained elevated, suggesting that the population of icy bodies extends significantly farther outward than previous surveys indicated. Complementary telescope observations from the Subaru telescope in Hawaii have discovered Kuiper Belt objects well beyond the 50 astronomical unit boundary, adding independent support to the idea that the belt is wider than we assumed. Some scientists have proposed that the main belt stretches to 80 astronomical units or beyond. Others suggest the data may point to a second, distinct Kuiper Belt beyond the first, a possibility that would reshape our picture of the outer solar system entirely. The implications for mission planning are significant. If the main belt truly extends to 80 astronomical units, then a spacecraft crossing the inner edge at 30 astronomical units has only entered the first third of the structure. Flying through the belt at New Horizons speed would take not 15 years but closer to 25, and the outer reaches would contain populations of objects that current surveys have not even begun to catalogue. The 2,000 catalogued trans-Neptunian objects may represent a vanishingly small sample of a much larger population, spread across a region far wider than anyone anticipated when the belt was first confirmed in the early 1990s. Either interpretation carries the same fundamental implication for the travel question. The frozen wilderness is even larger than we thought. the distances are even greater. The number of objects waiting to be explored is even higher, and the gap between what we have visited and what remains unseen grows more staggering with every new measurement. This is the reality that confronts anyone asking how long it takes to reach the Kuiper Belt. The question sounds simple. It invites a single number, a tidy answer, something you could fit on a poster and move on from. But the belt refuses to cooperate. It is too large, too varied, too poorly explored, and possibly even larger than current estimates allow. The distance to its inner edge is not the same as the distance to its center, which is not the same as the distance to its outer boundary, which is not the same as the distance to the most remote objects associated with it. Every honest answer depends on choices about targets, trajectories, speeds, and mission types. Those choices transform the travel time from a single figure into a spectrum that ranges from less than a decade to more than 3 centuries. But speculation only takes us so far. There is one mission that has actually made this journey. One spacecraft that launched from Earth, crossed the inner edge of the Kuiper Belt, visited 2 of its objects at close range, and is right now, as you listen to this, still traveling through the belt, recording data from deeper inside it than any human-built instrument has ever reached. It launched 2 decades ago. It flew faster than anything before it had ever left Earth. It carried instruments designed to operate in conditions no previous mission had faced. And even with all of that speed and preparation, its close encounters with the Kuiper Belt's worlds were measured in hours, not days. It could not slow down. It could not choose a different target once it was on its way. That mission does not provide a universal answer to the travel time question, but it gives us something far more valuable than any hypothetical calculation. It gives us an actual clock, a real timeline measured in real years by a real spacecraft burning real fuel across real distances. Its name is New Horizons, and its story is the closest thing we have to ground truth in a region of the solar system where certainties barely exist. Everything we know about how long it actually takes to reach the Kuiper Belt comes from a single spacecraft, not from calculations on a whiteboard, not from computer simulations, not from any theoretical model of what a future mission might accomplish with technology that does not yet exist. It comes from one real machine that left Earth, crossed billions of miles of empty space, and flew through the belt while human engineers tracked its every move. That machine is New Horizons, and its journey provides the only empirical timeline we have for measuring travel to the outer solar system. Before New Horizons, no spacecraft had ever been sent to the Kuiper Belt on purpose. The Voyager and Pioneer probes passed through the region decades earlier, but they were aimed at the giant planets, not at the icy worlds beyond Neptune. Their trajectories carried them through Kuiper Belt space as a side effect, not a mission objective. They carried no instruments optimized for studying small icy bodies at 40 or 50 astronomical units. They did not target any Kuiper Belt object for a close flyby. They did not even know the belt existed when they were launched. They passed through it the way a ship crosses an ocean without stopping at any island. The crossing happened, but it was not the point. New Horizons was different. It was built specifically to reach the Kuiper Belt, visit its most famous inhabitant, and return the first close-up data from this part of the solar system. Everything about its design, its trajectory, its instruments, and its timeline was shaped by one overriding constraint. The target was unimaginably far away, and the spacecraft had to get there before its nuclear power source decayed too far to operate its instruments. Every year of delay on the launch pad was a year of plutonium fuel lost to radioactive decay. The clock was ticking before the mission even left the ground. New Horizons launched on January 19, 2006, from Cape Canaveral, Florida. It lifted off aboard an Atlas V rocket, the most powerful configuration available at the time, fitted with 5 solid rocket boosters strapped to the first stage and a high-energy Centaur upper stage on top. A third stage, a solid-fuel kick motor, provided the final push after the Centaur finished its burn. The combined thrust of all 3 stages accelerated New Horizons to a departure velocity of approximately 36,000 miles per hour relative to Earth, making it the fastest spacecraft ever launched from this planet. Nothing humans had ever built had left Earth at that speed. For context, that velocity would carry you from New York to Los Angeles in under 5 minutes. New Horizons crossed the orbit of the Moon in just 9 hours. Most Apollo missions needed 3 days to cover the same distance. Within a year of launch, The spacecraft had already passed the orbit of Mars and was bearing down on Jupiter. The spacecraft itself was remarkably small for such an ambitious mission. New Horizons weighed roughly 1,054 pounds at launch, about the size and mass of a grand piano. It carried 7 scientific instruments packed into a compact frame, powered by a single radioisotope thermoelectric generator containing about 24 pounds of plutonium dioxide. That generator produced approximately 245 watts at launch, roughly enough to power 2 or 3 household light bulbs. By the time the spacecraft reached Pluto, radioactive decay had reduced the output to around 200 watts. Every instrument, every heater, every radio transmitter, every onboard computer drew from that diminishing supply. The mission was a race against entropy as much as distance. The velocity was not a luxury, it was a necessity. Pluto was roughly 3 billion miles away at the time of launch, and its orbit was carrying it farther from the Sun with each passing year. Pluto reached perihelion, its closest approach to the Sun, in 1989, and had been slowly receding outward ever since. As Pluto moved farther away, sunlight on its surface grew dimmer, and its thin nitrogen atmosphere began to cool and collapse, freezing onto the surface. Scientists wanted to study that atmosphere before it disappeared. Every year of delay meant a more distant target, a longer flight, a dimmer sun, and a thinner atmosphere. The urgency was real. Even at 36,000 miles per hour, the spacecraft could not reach Pluto on speed alone. The solar system is not a straight highway. A spacecraft launched from Earth must fight the Sun's gravity for the entire journey outward. As New Horizons climbed away from the Sun, gravity pulled it back, steadily reducing its velocity. Without additional help, the journey to Pluto would have taken more than 12 years using a minimum energy trajectory. That was too long. The atmosphere might be gone. The power source would be weaker. The scientific return would be diminished. The solution was Jupiter. 13 months after launch, on February 28, 2007, New Horizons flew past Jupiter at a closest approach distance of roughly 1.4 million miles. The encounter was not just a photo opportunity, though the spacecraft did capture stunning images of Jupiter's storms, rings, and moons that served as a full dress rehearsal for the Pluto instruments. The real purpose was gravitational. Jupiter's enormous mass, 318 times that of Earth, bent New Horizons' trajectory and accelerated it by roughly 9,000 miles per hour. That single gravitational slingshot shortened the trip to Pluto by approximately 3 full years. This is how gravity assists work, and understanding them is essential to understanding Kuiper Belt travel times. A spacecraft approaching a planet on a hyperbolic trajectory gains speed by stealing a tiny fraction of the planet's orbital momentum. The planet is so massive that it does not notice the loss. But for the spacecraft, the speed boost is transformative. It is free energy, requiring no fuel, no engine burn, no additional mass. The only cost is time and trajectory. The spacecraft must fly to the right place at the right time, passing the planet at exactly the right distance and angle to gain the desired velocity in the desired direction. Miss the window, and the assist is lost. Arrive at the wrong angle, and you get flung in the wrong direction. Jupiter is the most valuable gravity assist in the solar system because it is the most massive planet. A well-planned Jupiter flyby can add anywhere from 4 to 14 kilometers per second to a spacecraft's velocity, depending on the approach geometry. For New Horizons, Jupiter added roughly 4 kilometers per second, boosting the spacecraft's heliocentric velocity from approximately 19 to 23 kilometers per second. That boost does not sound dramatic in isolation, but over a journey spanning billions of miles, it translated into 3 fewer years of flight. The catch is that Jupiter is not always in the right position. Jupiter orbits the Sun once every 12 years, and the geometry required for an effective gravity assist toward a Kuiper Belt target only aligns during specific windows. For the Pluto mission, the optimal launch window opened in January 2006 and closed within weeks. If New Horizons had missed that window, the next opportunity for a Jupiter-assisted trajectory to Pluto would not have arrived for over a decade. The spacecraft would have had to fly a slower, less efficient path, arriving years later with less power remaining and a more distant, colder target. The entire scientific case for the mission depended on launching during that narrow window. This dependency on planetary alignment is one of the most underappreciated factors in Kuiper Belt travel times. A theoretical travel time calculated by dividing distance by speed is almost meaningless without accounting for gravity assists. No spacecraft currently in existence or under development can reach the outer Kuiper Belt in a reasonable time frame without at least one major gravity assist, and the availability of those assists is dictated by the orbital positions of Jupiter, and in some mission concepts, Saturn, a mission that launches when Jupiter is favourably positioned, might reach Pluto in 9 years. The same mission launched 3 years later, when Jupiter is on the wrong side of the Sun, might take 15. After the Jupiter encounter, New Horizons entered the longest and emptiest phase of its journey. The spacecraft spent most of the next 8 years in hibernation mode, its systems powered down to reduce wear on electronics and conserve the slowly diminishing power from its generator. It woke periodically, roughly once a year for about 2 months, for systems checks, software updates and trajectory corrections. During this cruise phase, there was almost nothing to observe. The spacecraft was crossing the vast, barren region between the orbit of Jupiter and the orbit of Pluto, a stretch of space containing no planets, no significant objects, and nothing worth turning the cameras on for. The emptiness was total. If you could somehow look out a window from New Horizons during those years, you would see nothing but stars, unchanging, week after week, month after month, year after year. The sun behind the spacecraft would gradually shrink from a brilliant disk to a dazzling point, growing dimmer with each passing year but never disappearing entirely. Meanwhile, mission controllers on Earth exchanged signals with the spacecraft that took progressively longer to arrive. At Jupiter, the one-way light time was about 45 minutes. By the time New Horizons passed the orbit of Saturn, the delay exceeded an hour. Crossing the orbit of Uranus, it climbed past 2.5 hours. Approaching Neptune's distance, the delay reached 4 hours, and as the spacecraft closed in on Pluto, radio signals took 4.5 hours to travel from Earth to the spacecraft, and another 4.5 hours to return. A simple question and answer between Mission Control and New Horizons required a 9-hour wait. This communication delay shaped everything about the mission's design. By the time New Horizons reached Pluto, real-time control was impossible. Sending a command and receiving confirmation that it was executed required a 9-hour round trip. Any problem that arose during the close flyby would be over long before Earth even knew it had happened. The spacecraft had to be programmed in advance with a detailed sequence of observations, maneuvers, and contingency responses. Every camera pointing, every spectrometer reading, every data recording was scripted days before the encounter. New Horizons flew past Pluto on autopilot, following instructions uploaded from Earth days earlier, with no possibility of real-time intervention. On July 14, 2015, 9 years and 5 months after launch, New Horizons made its closest approach to Pluto. The spacecraft passed within approximately 7,800 miles of the dwarf planet's surface, hurtling through the system at roughly 31,000 miles per hour relative to Pluto. The entire close encounter, the period during which the spacecraft's instruments could resolve surface features in meaningful detail, lasted approximately 1 day. The period of highest resolution, when images sharp enough to reveal features smaller than a city block were captured, lasted only a few hours. In those few hours, New Horizons transformed Pluto from a blurry dot into a world. The spacecraft revealed a landscape that no one had predicted. Vast plains of nitrogen ice, smooth and crater-free, stretched across a region shaped like a heart. Mountains of water ice towered more than 11,000 feet above the frozen plains, their peaks reaching heights comparable to the Rocky Mountains on Earth. Glaciers of nitrogen and carbon monoxide ice flowed through valleys and across crater floors. A thin but complex atmosphere of nitrogen, methane, and carbon monoxide extended far above the surface, layered in dozens of haze bands visible in backlit images as the spacecraft looked back after its closest approach. Those haze layers scattered sunlight in a way that turned Pluto's skies blue, a result no one had anticipated for a world so distant and so cold. The vast heart-shaped basin of nitrogen ice, informally named Tombau Regio after Pluto's discoverer, appeared to drive a rudimentary weather cycle, with nitrogen sublimating on the warmer sunlit side, circulating through the thin atmosphere and refreezing on the colder shadowed side in a slow planet-wide convection pattern that redistributed ice across the surface over centuries. A world receiving 1,600 times less sunlight than Earth had active weather and blue skies. Pluto was not a dead frozen rock. It was geologically active, atmospherically complex, and visually stunning. The data from that single flyby filled more than 50 gigabits of storage on the spacecraft's solid-state recorders, and it took 16 months to transmit all of it back to Earth at the glacially slow data rate of roughly 1 to 2 kilobits per second across 3 billion miles of space. But here is the part that matters for the travel time question. 9.5 years of flight, 3 billion miles of travel, a gravity assist from the largest planet in the solar system, the fastest launch velocity ever achieved from Earth. All of that effort, all of that time, all of that engineering, and the actual encounter with Pluto lasted less than a day. The spacecraft did not orbit. It did not slow down. It did not circle back for a second look. It flew past at 31,000 miles per hour and kept going. Within hours, Pluto was shrinking behind it. Within days, it was a dot again. Within weeks, it was indistinguishable from the background stars. New Horizons had spent nearly a decade getting there and spent less than 24 hours collecting close-range data. The ratio of travel time to observation time is staggering. Roughly 3,500 days of flight for 1 day of science. That ratio is not a quirk of mission design. It is a fundamental consequence of the distances involved and the speeds required to cross them. And New Horizons was not finished. While engineers were still downloading Pluto data, the spacecraft was already heading deeper into the Kuiper Belt. Its trajectory had been designed from the beginning to allow for at least one additional flyby target beyond Pluto. The challenge was finding one. New Horizons was traveling along a specific path through space, and it had very limited fuel remaining, enough for only modest course corrections of roughly 130 meters per second in total delta V. Any potential target had to lie almost exactly along the spacecraft's existing trajectory, close enough to reach without exceeding the remaining fuel budget. The search began years before the Pluto flyby. Astronomers used the Hubble Space Telescope and major ground-based observatories to scan the narrow corridor of sky ahead of New Horizons, looking for faint objects whose orbits would place them within reach. The search was extraordinarily difficult. The spacecraft's trajectory passed through a region near the galactic plane, where dense star fields containing millions of background stars made it nearly impossible to distinguish faint, slow-moving Kuiper Belt objects from the stellar clutter. The targets they were looking for would appear as points of light, roughly 100 million times dimmer than the faintest stars visible to the naked eye, drifting almost imperceptibly against the background over the course of hours. Hundreds of candidates were identified, tracked, and eliminated over months and years of observation. Most were too far from the spacecraft's path. Others had orbits too uncertain to guarantee a successful encounter. Some turned out to be background stars misidentified as moving objects. In June 2014, the Hubble team discovered a small object that appeared to lie almost directly in New Horizons' path. The body, initially designated 2014 MU69, and later officially named Arrokoth, was a cold, classical Kuiper Belt object orbiting at roughly 44 astronomical units. It was estimated to be only about 35 kilometers across, far smaller than Pluto and impossibly faint from Earth. Confirming its orbit required months of follow-up observations to establish a precise enough trajectory for the spacecraft to target. In November 2015, just 4 months after the Pluto flyby, New Horizons fired its thrusters to adjust its course by a fraction of a degree, setting itself on an intercept path with Arrokoth. On January 1st, 2019, 13 years after launch, New Horizons flew past Arrokoth at a distance of roughly 2,200 miles, making it the most distant planetary flyby in history. The spacecraft was approximately 4 billion miles from the Sun, 44 astronomical units out, deep in the heart of the classical Kuiper Belt. At that distance, radio signals took over 6 hours to reach Earth. The flyby occurred on New Year's Day, and the mission team at the Johns Hopkins Applied Physics Laboratory celebrated at midnight, knowing they would have to wait until the following evening to receive confirmation that the spacecraft had survived the encounter. What New Horizons found was unlike anything previously observed in the solar system. Arrokoth was a contact binary. Two roughly spherical lobes joined together like a snowman, each lobe reddish-brown and remarkably smooth. The larger lobe, roughly 22 kilometers across, was noticeably flatter than the smaller one. The object showed almost no impact craters, suggesting its surface had been largely undisturbed for billions of years. Its uniform color and texture indicated that Arrokoth had never been heated, never been fragmented, never experienced the violent collisions that shaped most objects in the inner solar system. Its shape told scientists something profound about how the building blocks of planets originally formed. The two lobes had not smashed together violently, they had drifted together gently, merging at low speed in the primordial solar nebula, like two soap bubbles touching and fusing. Arrokoth was a planetary fossil, preserved in the deep freeze of the outer solar system since the solar system's birth, the most pristine and unaltered object ever visited by a spacecraft. The encounter lasted hours, the close approach phase during which instruments gathered their most detailed data occupied a single frantic period measured in minutes and hours, not days. Then Arrokoth, like Pluto before it, receded behind the spacecraft. New Horizons continued onward. It could not stop, it could not turn around. It had visited two objects across 13 years of flight, spending a combined total of roughly 2 days in close-range observation. Pluto and Arrokoth. That is every close-range visit humanity has ever made to the Kuiper Belt. The sum total of our direct observation across 2 decades of mission operations amounts to less than 2 full days. Against a population estimated in the hundreds of thousands of objects larger than 100 kilometers, and possibly millions of smaller bodies, 2 flybys represent a sample so small it barely registers as a beginning. Everything we know about what these worlds actually look like, their surfaces, their compositions, their shapes, and their atmospheres or lack thereof, was gathered during those 2 brief windows of proximity. What makes the New Horizons timeline so instructive is what it reveals about the relationship between speed, distance, and target choice. The spacecraft reached Pluto at about 30 astronomical units in 9.5 years. It reached Arrokoth at 44 astronomical units in 13 years. The difference between those 2 flights, an additional 3.5 years, corresponds to an additional 14 astronomical units of distance. At New Horizons speed, every additional 10 astronomical units deeper into the belt costs roughly 3 more years of flight. Apply that ratio to other targets, and the travel times climb sharply. Reaching Mare at its average distance of about 46 astronomical units would take roughly 14 years at New Horizons speed, assuming a comparable trajectory and gravity assist. Reaching Mare at 43 astronomical units would take about 13 years. These targets lie within the main belt and are reachable within a single career span. But Eris, currently near 96 astronomical units, would require approximately 30 years. A scientist who launched that mission at age 35 would be 65 before the flyby occurred, and reaching Eris at aphelion, 98 astronomical units, would take slightly longer still. A mission to Sedna at perihelion, 76 astronomical units, would need over 23 years of continuous flight. These numbers assume a Jupiter gravity assist comparable to what New Horizons received. Without Jupiter's help, every figure increases dramatically. A spacecraft launched on a direct trajectory to Pluto without a gravity assist would need 12 to 14 years, not 9.5. A direct flight to Arrokoth would take 16 to 18 years, and a direct trajectory to Eris at 96 astronomical units might require 40 years or more. The gravity assist does not merely save time, it determines whether the mission is feasible within a human working lifetime. The dependency on Jupiter also means that mission planners cannot simply launch whenever they choose. Jupiter orbits the Sun every 12 years. The geometry required for an efficient gravity assist toward any specific Kuiper Belt target aligns only during certain windows within that 12-year cycle. For some targets, the window opens for a few weeks and then closes for over a decade. For others, the alignment never produces an efficient trajectory with currently available launch vehicles, meaning the target is effectively unreachable without a technological breakthrough in propulsion. Even when a window does open, the launch date must be precise. A delay of just a few days can degrade the gravity assist enough to add months or years to the flight. The outer solar system imposes its own schedule on exploration, a schedule dictated by orbital mechanics rather than human ambition, and that schedule is measured in years and decades, not months. New Horizons is still flying. As of late, 2024, the spacecraft had passed 60 astronomical units from the Sun, twice as far out as Pluto was during the 2015 flyby. It is travelling at roughly 14 kilometers per second relative to the Sun, covering approximately 3 astronomical units per year. At that speed, it crosses roughly 300 million miles of space annually, a distance greater than the gap between Earth and Mars. NASA extended the mission to continue operating until the spacecraft exits the Kuiper Belt, expected around 2028 or 2029. In its extended mission, New Horizons has shifted primarily to heliophysics observations, measuring the solar wind, charged particle environment, and dust density of the outer solar system. But the team continues searching for a potential third flyby target using ground-based telescopes and has not given up hope of one more close encounter before the spacecraft leaves the belt entirely. After that, New Horizons will continue outward into interstellar space, joining Voyager 1, Voyager 2, and the now silent Pioneer probes as one of only 5 human-made objects on trajectories that will carry them beyond the solar system. But New Horizons will never be able to stop. It has no ability to slow down significantly. Its remaining fuel is measured in meters per second of velocity change, not the kilometers per second that would be needed to enter orbit around anything. It will cross the outer boundary of the belt and keep going, gradually slowing as the Sun's gravity tugs against its outward motion, but never slowing enough to be captured by any body. Its power supply, a radioisotope thermoelectric generator loaded with plutonium, will continue to weaken at a rate of roughly 3 1/3 watts per year. Engineers estimate the spacecraft may remain operational until the mid-2030s, by which point it could be 90 to 110 astronomical units from the Sun. After that, New Horizons will fall silent, continuing its outward drift as a cold, dark artifact carrying the record of everything it learned during those 2 brief encounters with the frozen worlds of the Kuiper Belt. The New Horizons timeline tells us something that no equation can. It tells us what reaching the Kuiper Belt actually costs in human terms. Not just in fuel and engineering, but in time, patience, and the acceptance that years of effort buy only hours of proximity. 9.5 years to reach Pluto, 13 years to reach Arrokoth, both encounters measured in hours, both targets left behind forever. The spacecraft could not linger, could not return, could not choose a different path once it was on its way. It threaded a needle across 3 billion miles of space and then kept threading, heading deeper into the dark with no option to turn around. This is the reality of travelling to the Kuiper Belt with current technology. Speed buys you arrival but not exploration. A flyby gives you a glimpse, but not a survey. You can reach the belt's inner edge in a decade, its middle in 15 years, its far side in a quarter century, but at every distance, the encounter is brief and the departure is permanent. The spacecraft arrives fast, gathers what it can in a window measured in hours, and then vanishes outward into the void, carrying its data and its silence into deeper and deeper space. And yet speed is only half the equation. Everything New Horizons accomplished, every image of Pluto's mountains, every measurement of Arrokoth's shape, every particle of data transmitted back to Earth, was collected during a flyby. The spacecraft never stopped. It never orbited. It never had the option. Stopping at a Kuiper Belt object is a fundamentally different problem from reaching one, and it is a problem that current engineering has barely begun to solve. What comes next is the part of the story where the physics turns brutal. Getting to the Kuiper Belt is hard. Staying there is almost impossible. This distinction sounds like semantics, but it is the single most important engineering divide in all of outer solar system exploration. Flying past a Kuiper Belt object at 31,000 miles per hour, the way New Horizons flew past Pluto, requires speed, precision, and patience. Entering orbit around that same object, staying there long enough to map its surface, study its composition, and observe its behavior over weeks or months, requires something far more difficult. It requires slowing down, and slowing down in the outer solar system is a problem that no mission has ever solved and that current technology can barely approach. On Earth, stopping is easy. You hit the brakes and friction does the work. A car on a highway bleeds speed through its brake pads. A boat in water slows down the moment the engine cuts because the water resists its motion. A skydiver deploys a parachute and air drag decelerates the fall. Every method of stopping that humans use in daily life relies on a medium, something to push against, something that absorbs kinetic energy and converts it to heat. Space has no medium. There is no air. There is no water. There is no surface to drag against. A spacecraft traveling at 14 kilometers per second will continue traveling at 14 kilometers per second forever, unless a force acts on it. In the vacuum between planets, the only force available is thrust from an onboard engine, and thrust requires fuel, and fuel has mass, and mass is the enemy of everything in spaceflight. This is where the physics turns cruel. To slow a spacecraft from a high-speed flyby trajectory into a stable orbit around a Kuiper Belt object, you need to cancel most of the spacecraft's velocity relative to that object. The amount of velocity change required is measured in what engineers call delta V, a term that simply means change in speed. For New Horizons at Pluto, the relative velocity was roughly 14 kilometers per second. To enter orbit around Pluto, the spacecraft would have needed to shed nearly all of that speed, reducing its velocity relative to Pluto to perhaps a few hundred meters per second. That means a delta V of roughly 12 to 13 kilometers per second. In raw numbers, this does not sound outrageous. Spacecraft routinely perform maneuvers involving several kilometers per second of delta V. The problem is how much fuel it takes. The relationship between delta V and fuel mass is not linear, it is exponential. This is the most unforgiving equation in all of rocketry, and it governs every mission ever flown beyond low Earth orbit. To achieve a given delta V, a spacecraft must carry fuel, but that fuel has mass, and that additional mass itself requires fuel to accelerate, which adds more mass, which demands still more fuel. The cycle feeds on itself. The result is that each additional kilometer per second of delta V requires a disproportionately larger quantity of propellant. A spacecraft that needs 1 kilometer per second of delta V might need to carry fuel equal to about 40% of its total mass. Double that to 2 kilometers per second, and the fuel fraction climbs to roughly 65%. At 5 kilometers per second, the spacecraft must be more than 80% fuel by mass. At 10 kilometers per second, it approaches 95%. And at the 12 to 13 kilometers per second needed to stop at Pluto from a New Horizons-like trajectory, the numbers spiral into absurdity. Using conventional chemical propulsion, the fuel mass required would be dozens of times the mass of the rest of the spacecraft. You would not be launching a science probe. You would be launching a fuel tanker that happened to carry a camera. The arithmetic is pitiless. To put this in concrete terms, New Horizons weighed roughly 1,054 pounds at launch. To carry enough chemical fuel to decelerate into orbit around Pluto from its flyby velocity, the spacecraft would have needed to weigh tens of thousands of pounds at departure, possibly exceeding 100,000 pounds depending on the specific propellant and engine performance. No existing rocket could have launched that combined mass on a trajectory to the outer solar system. Even the most powerful rocket currently operational could not lift that much weight to Jupiter, let alone to Pluto. The entire mission architecture would have buckled under the weight of its own propellant. This is why New Horizons was designed as a flyby from the very beginning. Not because scientists preferred a brief encounter over a long one, but because stopping was physically impossible with any technology available then or now using chemical engines alone. The exponential fuel problem applies to every conceivable Kuiper Belt orbiter mission. The faster you travel to the belt, the more delta V you need to stop when you arrive. But travelling slowly to reduce the stopping requirement means the journey takes far longer, which brings its own set of engineering problems. Power sources decay, electronics age, funding cycles end. Scientists retire. A slow trajectory that takes 25 or 30 years to reach Pluto reduces the arrival speed and the fuel needed to stop, but it means the spacecraft's nuclear generator has lost a quarter of its power output before the mission even begins its primary science phase. The mission must carry instruments that still function after decades of radiation exposure, thermal cycling, and component degradation. Every additional year of cruise adds risk, complexity, and cost. There is an alternative to chemical propulsion that fundamentally changes the fuel equation. Electric propulsion, sometimes called ion propulsion, works by using electric fields to accelerate charged atoms or molecules, typically xenon gas, to extremely high exhaust velocities. These engines are vastly more fuel efficient than chemical rockets. Where a chemical engine might expel exhaust at 4 or 5 kilometers per second, an ion engine can achieve exhaust velocities of 20 to 50 kilometers per second or more, sometimes approaching 100 kilometers per second in advanced designs. This means the same amount of fuel produces far more delta V. The exponential fuel penalty still applies, because the underlying physics cannot be avoided, but the higher exhaust velocity shifts the curve so dramatically that missions requiring 10 or 12 kilometers per second of delta V become manageable. An ion-powered spacecraft might carry 30 to 40% of its mass as propellant rather than 95%. That is the difference between a mission that can be built and one that cannot. The catch is thrust. Ion engines produce extremely low force, typically measured in fractions of a newton. For comparison, a chemical rocket engine like those used on spacecraft orbital insertion burns can produce hundreds or thousands of newtons, enough to change a spacecraft's velocity by several kilometers per second in minutes. An ion engine might produce 1/10 of a newton, barely enough to accelerate a sheet of paper on a frictionless surface. This minuscule force must be applied continuously over months or years to accumulate the desired velocity change. An ion engine cannot perform a quick braking burn the way a chemical engine can. Instead, it decelerates the spacecraft gradually, like a gentle headwind applied for years, rather than a sudden collision with a wall. The spacecraft does not arrive and stop. It approaches slowly, bleeding speed across an extended arc of deceleration that might span hundreds of millions of miles. The total delta V achieved can be enormous, but the time required to achieve it transforms the mission timeline from years into decades. In 2020, a team of researchers published the first detailed mission design study for a combined Pluto orbiter and Kuiper Belt explorer using electric propulsion. The study demonstrated that such a mission is technically feasible with present-day technology, assuming one critical advancement. The electric propulsion system would need to be powered by a radioisotope thermoelectric generator, using the heat from decaying plutonium to generate the electricity that drives the ion engines. This has never been demonstrated in flight, but the researchers assessed it as a low-risk capability within current engineering. The mission concept used a conventional chemical rocket to launch the spacecraft and a Jupiter gravity assist to send it toward the outer solar system, then switched to electric propulsion for the long, slow deceleration as it approached the Pluto system. The study found that the spacecraft could enter orbit around Pluto and conduct a comprehensive survey of the entire system, including close-up studies of Charon and the 4 smaller moons, Nix, Hydra, Kerberos, and Styx. An orbiter could observe Pluto through all seasons and lighting conditions, map the entire surface at high resolution rather than the single hemisphere New Horizons captured, monitor weather patterns and atmospheric changes over years, and study how nitrogen ice migrates across the surface in response to the faint but measurable cycle of Pluto's seasons. The scientific return from an orbiter would be comparable to what Cassini achieved at Saturn, or what the Mars Reconnaissance Orbiter continues to achieve at Mars, a comprehensive, multi-year portrait that transforms a world from a collection of snapshots into a fully understood planet. But the total mission duration was staggering, approximately 75 years from launch to completion. The travel time to Pluto alone, using the slow, fuel-efficient electric propulsion trajectory, would be measured in decades rather than the 9.5 years New Horizons achieved. The spacecraft would spend years decelerating as it approached, trading speed for the ability to stop, and even after entering orbit, the low-thrust propulsion system would need years more to maneuver through the Pluto system, using a combination of electric propulsion burns and gravity assists from Charon to change its orbital parameters. The Charon assist concept is one of the study's most innovative ideas. Charon, Pluto's largest moon, orbits at a distance of roughly 12,000 miles from Pluto, with an orbital period of about 6.5 days. By timing orbital passes near Charon, a spacecraft can use the moon's gravity to adjust its trajectory within the Pluto system without burning fuel. Each Charon flyby bends the spacecraft's path slightly, allowing it to change its orbital altitude, inclination, or eccentricity. Over many such passes, the spacecraft can explore different aspects of the Pluto system from varying geometries, all without the massive fuel expenditure that powered maneuvers would require. Eventually, a carefully planned sequence of Charon gravity assists can even accelerate the spacecraft back to escape velocity, freeing it from Pluto's gravitational grip and sending it back into the Kuiper Belt to visit another target. This is an elegant solution, but it takes years to execute. Each Charon encounter occurs once every 6.5 days, and dozens of encounters may be needed to achieve the desired orbital changes. Patience, measured in years rather than hours, becomes the mission's defining characteristic. 75 years. Consider what that duration means in human terms. A mission launched today under this architecture would not complete its objectives until approximately the year 2100. The scientists who conceived and designed it would not live to see its final results. The engineers who assembled and tested the spacecraft would be gone long before the orbital survey was finished. The graduate students who analyzed the early cruise data would be elderly retirees when the last observations arrived from Pluto orbit. The mission would span 3 or 4 generations of researchers, each inheriting the institutional knowledge, the software tools, the communication protocols, and the scientific questions of the previous generation, and passing their own contributions to the next. No space mission in history has operated on that timescale. The longest-running active deep space missions, the Voyager spacecraft, have been operating for roughly 48 years as of 2025, and they are profoundly simpler by comparison. They carry far fewer instruments, perform far less complex operations, and execute far fewer maneuvers than a Pluto orbiter would require across its 75-year lifespan. Maintaining the institutional commitment, the funding pipeline, the workforce continuity, and the political will to sustain a single mission across most of a century is arguably a harder problem than the engineering itself. The engineering challenges of a decades-long mission to the outer solar system extend far beyond propulsion. Every component aboard the spacecraft must survive for a human lifetime in conditions that are hostile to machines and materials alike. Temperatures in the Kuiper Belt are savage. At Pluto's distance, the ambient temperature of surrounding space hovers near -230 degrees Celsius, only about 40 degrees above absolute zero. At these temperatures, metals become brittle. Lubricants freeze solid. Electrical connections contract and can develop microscopic cracks over time. Electronic components, mechanical actuators, optical instruments, and communication systems must all function reliably after decades of continuous exposure to this deep cold. Some components must be kept warm through active heating just to survive, let alone operate. Thermal management becomes one of the mission's most critical and power-hungry systems. Electric heaters must keep sensitive electronics above their minimum operating temperatures, batteries above their freezing points, and propellant lines above the point where fuel would solidify. Those heaters draw power from the slowly weakening nuclear generator. Every year, the generator's output drops by roughly 3 to 4 watts as the plutonium fuel decays. Over 20 years, that loss exceeds 60 watts, a devastating fraction of the already tiny power budget. Over 50 years, more than half the original power may be gone. Engineers must plan for this decline from the beginning, designing systems that can progressively shed non-essential loads as the power shrinks. They face increasingly painful choices about which instruments to keep warm and running, which to power down into cold storage, and which to abandon entirely. A 75-year mission would test these trade-offs to a degree no previous spacecraft design has ever attempted. Radiation is another relentless adversary. Cosmic rays, high-energy particles originating from supernova explosions and other violent events beyond the solar system, bombard the spacecraft continuously throughout its journey. Over decades, these particles accumulate damage in electronic circuits, flipping bits in memory, degrading transistors, and slowly eroding the performance of processors, sensors, and data storage systems. The cumulative radiation dose over a 75-year mission would far exceed anything a spacecraft in Earth orbit, or even in Jupiter's radiation belts, would experience over a shorter lifetime. Spacecraft designers account for this by using radiation-hardened components, but even hardened electronics have lifetime limits. A mission lasting 75 years would push those limits further than any previous design has attempted. Redundancy helps. Carrying backup systems for critical functions extends the probable operational lifetime, but redundancy adds mass, and mass is the quantity that every aspect of the mission fights to minimize. Communication across Kuiper Belt distances presents its own brutal constraints. At Pluto's distance from Earth, a radio signal traveling at the speed of light takes approximately 4.5 to 5 hours to arrive. At 50 astronomical units, the outer edge of the main belt, the one-way delay exceeds 7 hours. At Eris, near 96 astronomical units, it stretches past 13 hours. A single round-trip exchange, sending a question and receiving an answer, would take more than a full Earth day. These delays make real-time communication impossible, but the greater problem is not latency. It is bandwidth. The strength of a radio signal decreases with the square of the distance. Double the distance and the signal becomes 4 times weaker. Triple it and the signal drops to 1/9. At Pluto's range, New Horizons transmitted data at roughly 1 to 2 kilobits per second, a rate so slow it is difficult to grasp in an era of broadband internet. Downloading a single high-resolution photograph took hours. Downloading the full dataset from the Pluto flyby, roughly 50 gigabits, took 16 months of continuous, around-the-clock transmission. An orbiter conducting years of observations would generate vastly more data, potentially hundreds of times more, and transmitting it all back to Earth at these cripplingly slow rates would require either a communication architecture far beyond what any existing deep space mission has used, or an acceptance that much of the data would never be returned. Larger antennas on the spacecraft and on Earth, higher transmission power, advanced data compression, or entirely new communication technologies like optical laser links would all be needed to make comprehensive data return feasible. Each of these solutions adds mass, power consumption, complexity, and cost to a mission already straining against every physical limit. Navigation at extreme distances adds yet another layer of difficulty. Spacecraft navigate by tracking their radio signals from Earth, and by using onboard star trackers and cameras to identify their position relative to known celestial references. At Kuiper Belt distances, the precision of Earth-based tracking degrades because the signal travel time introduces larger uncertainties. Onboard navigation becomes more important, but the targets themselves are poorly characterized. Many Kuiper Belt objects have positions known only to within thousands of kilometers, which is far too imprecise for a spacecraft attempting to enter orbit. A flyby mission can compensate with last-minute trajectory corrections, but an orbiter must know its target's position and mass to extraordinary precision months or years in advance to plan the deceleration correctly. Errors in the target's estimated mass would cause the spacecraft to enter the wrong orbit or miss the capture entirely. Obtaining that precision requires extensive observations from Earth-based and space-based telescopes before the mission even launches, observations that may take years to complete for any given Kuiper Belt target. There is one more factor that makes Kuiper Belt orbiter missions uniquely challenging. There is no large planet nearby to help with braking. When spacecraft enter orbit around planets like Mars, Jupiter, or Saturn, they benefit from the target's own substantial gravity. Mars has enough gravitational pull that a spacecraft can enter orbit with a relatively modest engine burn. Jupiter and Saturn are so massive that their gravity assists can reshape trajectories dramatically. Even for moons like Titan, the parent planet provides a gravitational framework that simplifies orbit insertion. A spacecraft entering the Saturn system, for example, can use Saturn's gravity to slow down and then maneuver between Saturn's moons using a series of gravity assists, the way the Cassini mission did for 13 years. The Kuiper Belt has no such infrastructure. Its objects are small and profoundly isolated. Pluto's mass is roughly 1/5 of 1% of Earth's mass, about 1/6 of the mass of Earth's moon. Its gravitational pull is so feeble that a spacecraft approaching at anything more than a slow-walking pace, cosmically speaking, barely notices it. Pluto cannot meaningfully slow down a probe the way Jupiter or Saturn can slow visiting spacecraft. The spacecraft must bring all of its deceleration capability with it, carrying the fuel or the electric propulsion system needed to cancel its own velocity with no gravitational help from the target. This self-sufficiency requirement drives up the mission mass, complexity, and cost far beyond what inner solar system missions require. Even the concept of aerobraking, one of the most valuable fuel-saving techniques in planetary exploration, is completely unavailable anywhere in the Kuiper Belt. Aerobraking uses a planet's atmosphere to slow a spacecraft through aerodynamic drag. The spacecraft skims through the upper atmosphere on each orbital pass, converting velocity into heat, gradually lowering its orbit over weeks or months without burning a drop of fuel. Mars orbiters have used this technique routinely and successfully, saving thousands of kilograms of propellant and enabling missions that would otherwise be impossible. The technique has been proposed for future missions to Titan and Venus, where thick atmospheres would allow rapid deceleration. But Pluto's atmosphere, thin as it is, provides far too little resistance to slow a spacecraft meaningfully. The surface pressure on Pluto is roughly 100,000 times lower than Earth's at sea level. A spacecraft flying through Pluto's atmosphere at orbital velocity would experience less drag than a feather dropped in a near-perfect vacuum chamber. The effect would be immeasurable, and most other Kuiper Belt objects have no atmosphere at all. Arrokoth has none. Marke appears to have at most an extremely thin and tenuous envelope. Haumea has none detected. Eris may possess a thin, seasonally frozen atmosphere that collapses onto its surface when it is far from the Sun, but even at its thickest, it would be negligible for braking purposes. Aerobraking is not merely impractical at the Kuiper Belt, it is physically meaningless. The absence of aerobraking, the absence of large gravitational helpers, the extreme distances, the communication delays, the crippling cold, the decaying power sources, and the exponential fuel penalty combine to create a problem that is qualitatively different from anything encountered in inner solar system exploration. Sending an orbiter to Mars requires overcoming distance and precision. Sending an orbiter to the Kuiper Belt requires overcoming distance, precision, time, energy, communication, temperature, power, fuel mass, and the simple biological fact that human careers are shorter than the missions demand. This does not mean a Kuiper Belt orbiter is impossible. The 2020 study proved it is technically feasible, at least for Pluto, the nearest and most accessible major Kuiper Belt target. But Pluto is the easy case. Consider what an orbiter mission to Eris would require. Eris currently sits near 96 astronomical units, more than 3 times farther than Pluto at its closest. The travel time would be correspondingly longer. The communication delay would exceed 13 hours each way. The sunlight available for observations would be roughly 1/9 what it is at Pluto, already desperately faint. The nuclear generator would have decayed for decades longer during the extended cruise. An orbiter mission to Eris using electric propulsion might require well over a century from launch to completion, a timeline that no human institution has ever sustained for any project of any kind. Even for targets within the main belt, like Marke at 46 astronomical units or Haumea at 43, orbiter missions would still require multi-decade commitments that dwarf anything in the current space exploration portfolio. The cost of an orbiter is measured not in billions of dollars alone, but in decades of institutional commitment, multiple generations of scientists, and technology that must function for longer than most human organizations survive. The contrast with a flyby is stark. New Horizons reached Pluto in 9.5 years, conducted its flyby in hours, and began returning data almost immediately. A Pluto orbiter would take decades to arrive, spend years conducting its survey, and require decades more of data transmission. The scientific return from an orbiter would be orders of magnitude greater, providing the kind of comprehensive long-duration study that transformed our understanding of Mars, Jupiter, and Saturn. But the price in time is staggering. The Kuiper Belt demands a choice. Fly fast and see little, fly slow and see everything, but wait a lifetime for the results. There is no middle path with current technology. The physics of braking in deep space, the weakness of Kuiper Belt gravity fields, and the exponential cost of carrying fuel all conspire to make speed and thoroughness mutually exclusive. A fast mission cannot stop. A stopping mission cannot be fast. The outer solar system does not offer compromises. Future propulsion technologies might eventually shift this equation. Nuclear thermal propulsion, which uses a nuclear reactor to heat hydrogen propellant to extreme temperatures, could achieve exhaust velocities 2 to 3 times higher than chemical rockets. reducing the fuel penalty for high delta-V maneuvers. Solar sail concepts, using the pressure of sunlight on enormous reflective membranes, could theoretically accelerate spacecraft without any fuel at all, though the sunlight at Kuiper Belt distances is far too faint to provide useful thrust for deceleration. More speculative ideas, including fusion propulsion, antimatter drives, and laser-push sails, exist on paper but remain decades from practical implementation. None of these are available today. None are funded for development on timelines relevant to near-term Kuiper Belt missions. The outer solar system waits, indifferent to our ambitions, while the engineering catches up. For now, the reality is simple and unforgiving. We can reach the Kuiper Belt. We have proven that. We can fly past its objects at tremendous speed and capture data during encounters lasting hours. We have proven that too. But we cannot stay. We cannot orbit. We cannot linger long enough to study any Kuiper Belt world the way we have studied Mars or the moons of Jupiter and Saturn. Every flyby that has ever been conducted at the Kuiper Belt lasted hours. Every orbiter concept that has ever been seriously studied requires decades. The gap between those two numbers, hours of actual observation versus decades of mission duration, is the gap that defines the frontier, and closing that gap is one of the hardest unsolved problems in all of human spaceflight. What remains then is to reckon with what this means, not with the engineering which will advance, not with the propulsion which will improve, but with the scale of what the Kuiper Belt actually contains, how little of it we have touched, and what it means to explore a frontier where even our greatest achievements barely scratch the surface. Step back far enough, and the numbers become a kind of confession. The Kuiper Belt contains, by conservative estimate, hundreds of thousands of objects, larger than 100 kilometers in diameter. Some models push the count higher, into the millions when you include objects down to a few kilometers across. The total population of icy bodies orbiting between 30 and 50 astronomical units may number in the billions when you count every frozen fragment down to the size of a house. Each of these objects is a world in miniature. Each has a surface shaped by billions of years of bombardment, sublimation, and cosmic ray exposure. Each carries chemical clues about the conditions that existed in the outer solar nebula 4.5 billion years ago, when the sun was young and the planets were still assembling themselves from a spinning disk of gas and dust. These are not empty rocks drifting through the void. They are frozen archives, the most pristine samples of the early solar system that still exist anywhere. In the inner solar system, the original building blocks of the planets were long ago consumed, melted, differentiated, and recycled by geological processes. Earth's surface has been overwritten hundreds of times by volcanism, plate tectonics, erosion, and life itself. Even the asteroids between Mars and Jupiter have been heated, fragmented, and reassembled by billions of years of collisions. But in the Kuiper Belt, far from the sun's warmth, the original material has been preserved in deep freeze. These objects formed in the cold outer reaches of the solar nebula and have remained there ever since, barely altered, their surfaces recording conditions that vanished everywhere else billions of years ago. They hold answers to questions about planetary formation, the delivery of water and organic molecules to the inner solar system, and the chemical processes that may have set the stage for life on Earth. And we have barely begun to read what they contain. We have visited 2 of them, 2 objects out of hundreds of thousands, 2 flybys out of a structure spanning billions of miles, 2 brief encounters, each measured in hours, across a combined 20 years of mission operations. Pluto and Arrokoth. That is the complete inventory of humanity's close-range experience with the Kuiper Belt. Everything else we know about this region, every other object, every other surface, every other composition, every other orbit, comes from telescope observations made at distances of billions of miles. We have studied the belt the way someone might study an ocean by standing on the shore with binoculars. We have seen shapes. We have measured brightnesses. We have inferred compositions from the faint spectra of reflected sunlight, but we have touched almost nothing. The worlds we have never visited are not duplicates of the 2 we have seen. The Kuiper Belt is not a uniform collection of identical icy bodies scattered through the dark. It is startlingly, almost bewilderingly diverse. Pluto turned out to be geologically active, with flowing glaciers, towering mountains, and a complex layered atmosphere. Arrokoth turned out to be a pristine contact binary, untouched since formation, a relic from the earliest moments of planetary accretion. No one predicted either result before the encounters. The belt surprised us both times, and there is no reason to think it will stop surprising us. Consider the worlds we have never seen up close. Eris is nearly Pluto's twin in size, but 27% more massive, suggesting a denser, rockier interior. Its surface is among the most reflective in the solar system, coated in a layer of frozen nitrogen and methane, so bright that it rivals fresh snow. Something is resurfacing Eris, keeping it pristine despite billions of years of cosmic ray bombardment that should darken exposed ices. We do not know what that process is. We have never been close enough to find out. Marke is the second brightest object typical after Pluto. It appears reddish, coated in methane and possibly ethane ices. In 2016, astronomers discovered it has a small, dark moon. The presence of a moon allows precise mass measurements, which indicate Marke is less dense than Pluto, suggesting a different internal structure, perhaps more ice and less rock. But the details of its surface, its geology, its possible seasonal atmosphere all remain unknown. No spacecraft has ever pointed a camera at it from closer than several billion miles. Haumea is one of the strangest objects in the entire solar system. It is not round. It is elongated, shaped roughly like an ellipsoid, spinning end over end once every 4 hours, one of the fastest rotational periods of any known large body. Its rapid spin suggests it was struck by a massive impact long ago, an event violent enough to reshape its entire structure and eject fragments that now orbit as a family of smaller objects sharing similar orbits. Haumea has 2 known moons and a faint ring system, the first ring ever detected around a trans-Neptunian object. Its surface is covered in nearly pure water ice, unusual among Kuiper Belt objects that are typically coated in darker organic material. Something about Haumea's formation, or its violent collisional history, made it fundamentally different from its neighbours, and we have no close-range data whatsoever to explain why. Quaoar, a body roughly half the diameter of Pluto, orbits at about 43 astronomical units and shows evidence of past cryovolcanism, the eruption of icy slurries and vapours rather than molten rock from its interior. Its surface contains both water ice and what appear to be deposits of crystalline ice that should have been destroyed by cosmic radiation over billions of years, suggesting the surface has been refreshed relatively recently in geological terms. Even more remarkably, astronomers discovered in 2023 that Quaoar possesses a ring system orbiting at a distance that should be impossible according to classical physics. The ring lies well beyond the body's Roche limit, the distance within which tidal forces should prevent ring material from clumping together into a moon. Its existence challenges fundamental assumptions about how rings form and survive around small bodies. No spacecraft has ever been close enough to image this ring directly, and understanding it may require a visit. Arrokoth, sometimes called the anti-Pluto, because its orbit is nearly a mirror image of Pluto's path, locked in the same resonance with Neptune but offset by half an orbital period, has a proportionally large moon named Vanth. The Arrokoth and Vanth system may be tidally locked, with both bodies permanently showing the same face to each other, as Pluto and Charon do. Its surface appears to contain water ice mixed with ammonia and possibly methane, hinting at a complex chemical history. Varuna is a large, rapidly rotating body that appears elongated by its own spin, stretched into an oblong shape that suggests it has very low internal strength, perhaps a loose rubble pile barely held together by its own feeble gravity. Each of these worlds poses questions that telescope observations alone cannot answer. Each would transform our understanding of the outer solar system if visited by a spacecraft, and each remains, for now, nothing more than a faint point of light in the world's largest telescopes. The variety matters because it means the Kuiper Belt cannot be understood by visiting 1 or 2 representative objects. Pluto is not typical of the belt. It is the largest object, the most massive, the most geologically complex. Drawing conclusions about the entire Kuiper Belt from Pluto would be like drawing conclusions about all the continents from a single visit to Antarctica. Arrokoth is more representative of the cold classical population, the small, undisturbed bodies that make up the bulk of the belt's membership. But even Arrokoth may not be typical. It was selected for the New Horizons flyby partly because it was the only reachable object along the spacecraft's trajectory. Its properties may or may not represent the broader population. We simply do not have enough data points to know. This ignorance extends to fundamental questions about the belt's structure, history, and boundaries. We do not know how many dwarf planets exist beyond Neptune. The official count of recognized dwarf planets in the Kuiper Belt is 4. Pluto, Eris, Marke, and Haumea, but astronomers strongly suspect there are many more. Estimates range from dozens to over 100 objects large enough to be rounded by their own gravity, orbiting in the outer solar system awaiting discovery. Many of these potential dwarf planets are too faint to detect with current telescopes because they orbit at extreme distances, have low surface reflectivity, or both. Some may be comparable in size to Pluto. Others may be smaller but geologically fascinating in ways we cannot predict. We would not know what they are until we found them, and finding them requires either more powerful telescopes or patient surveys spanning decades of observation. We do not know the true extent of the belt. Evidence from New Horizons dust counter and from ground-based telescope discoveries suggests the belt may stretch far beyond its assumed 50 astronomical unit outer boundary, possibly to 80 astronomical units or farther. But the census of distant objects remains desperately incomplete. Faint, faraway bodies reflect almost no sunlight, move almost imperceptibly against the background stars, and require exposures of hours on the largest telescopes in the world to reveal themselves. The Vera Rubin Observatory, a powerful new survey telescope in Chile expected to begin full operations in the near future, will dramatically improve our ability to detect distant Kuiper Belt objects by scanning the entire visible sky repeatedly every few nights. But even this remarkable instrument will detect only the larger and brighter objects at extreme distances. The smaller, darker, more distant inhabitants of the belt will remain hidden for years or decades to come. We do not know how the belt's composition varies with distance. Inner belt objects appear to be redder and contain more complex organic compounds on their surfaces. Outer objects may be icier and less processed. This color gradient may trace the chemistry of the original solar nebula, where temperatures and radiation levels varied with distance from the young sun, producing different mixtures of ices and organic compounds at different orbital radii. Understanding whether this gradient is real and continuous or patchy, and disrupted by Neptune's ancient migration, would tell scientists something fundamental about how the outer solar system assembled itself. But resolving the question requires spectral measurements far more detailed than ground-based telescopes can achieve at these distances. The objects are too faint, too cold, and too far away for current instruments to distinguish subtle compositional differences reliably. What telescopes detect is an average, a smear, not the fine-grained chemical portrait that only a visiting spacecraft could provide. The sample behind this pattern amounts to a few hundred objects out of a population estimated in the hundreds of thousands. It is as if someone scraped a few grains from a frozen lake and tried to map the chemistry of the entire body of water from that alone. The compositional map of the Kuiper Belt is almost entirely blank, and no current mission in any agency's pipeline is designed to fill it in. We do not even know whether the belt contains large objects that have so far escaped detection entirely. The possibility of a distant, undiscovered planet in the outer solar system, sometimes referred to informally as Planet 9, remains scientifically open and actively debated. The orbits of several extreme trans-Neptunian objects, including Sedna, show spatial alignments and clustering patterns that some researchers interpret as evidence for the gravitational influence of a massive planet, perhaps 5 to 10 times Earth's mass, orbiting at distances of several hundred astronomical units on a highly elongated path. Others argue the apparent alignments are observational artifacts, products of biased telescope surveys that preferentially detect objects in certain regions of the sky. The question remains open. If such a planet exists, it would fundamentally reshape our understanding of the outer solar system's structure and history. And we cannot rule it out because we simply have not observed enough of the Kuiper Belt to say what it does or does not contain. This is the state of our knowledge. After 33 years of Kuiper Belt science, counting from the first confirmed discovery in 1992, we have catalogued roughly 2,000 objects out of a population estimated in the hundreds of thousands. We have measured orbits for most of those 2,000 catalogued objects but detailed physical information, size, shape, composition, rotation period, the presence of moons, exists for only a small fraction. We have obtained spectra revealing surface composition for perhaps a few hundred. We have visited 2. We have obtained close-range data from those 2, totaling approximately 48 hours of observation across 20 years of mission operations. We have photographed one hemisphere of Pluto in high resolution and captured a few dozen images of Arrokoth. The rest of the belt, its hundreds of thousands of worlds, its potential dwarf planets, its compositional gradients, its structural boundaries, its possible extended region beyond 50 astronomical units, remains known only through the faint light that trickles across billions of miles of empty space to reach our telescopes. We are not ignorant of the Kuiper Belt, but our knowledge is thin, built from remote observations and 2 brief encounters, stretched across a region so vast that the known objects represent a coverage so sparse it would be invisible on any honest map. What does near-term exploration of the Kuiper Belt realistically look like? Not like a fleet of spacecraft fanning out across the belt. Not like an orbiter arriving at Pluto within a generation. Not like anything resembling the pace of inner solar system exploration, where multiple rovers, orbiters and landers visit Mars in a single decade and missions to Jupiter and Saturn launch every few years. The Kuiper Belt is too far, too expensive to reach, and too poorly understood to support rapid exploration with current budgets and technology. Each mission requires its own dedicated launch vehicle, its own gravity assist, its own decade-long cruise, and its own nuclear power source. The infrastructure that makes inner solar system exploration routine, reusable trajectories, reliable gravity assists, solar power, fast communication, simply does not exist in the outer solar system. The most realistic near-term possibility is another flyby mission, a New Horizons successor designed with improved instruments, a more powerful communication system, and possibly a faster trajectory achieved through advanced propulsion or a more favourable gravity assist geometry. Such a mission could target one of the major dwarf planets that no spacecraft has ever visited. Marquet, Haumea, Quaoar, or possibly Eris, if a favourable launch window and Jupiter alignment can be identified. Travel times would range from 12 to 30 or more years depending on the target and trajectory. The scientific return would be transformative for each target, turning another fuzzy dot into a fully realised world with known geology, composition, and atmospheric properties. But such a mission would require a budget exceeding $2 billion, a development timeline of 10 to 15 years before launch, and an operational commitment spanning decades of flight and data return. By comparison, NASA launches a major Mars mission roughly every 2 to 3 years at costs that are often lower. The outer solar system does not scale the way the inner solar system does. Every Kuiper Belt flyby is a flagship-class investment for a few hours of close-range science. But the encounter would still be a flyby. Hours of close observation after years or decades of flight. One more data point added to a catalogue that needs hundreds. Multiple flyby missions targeting different objects at different distances and orbital types would begin to build the statistical foundation that Kuiper Belt science desperately lacks. If we could visit 10 or 20 objects across several decades of sustained exploration, we could begin to understand whether Pluto is an anomaly or a representative example, whether Arrokoth's pristine surface is common or unusual among cold classical objects, whether the belt's composition truly varies with distance in the way remote observations suggest, whether scattered disk objects differ fundamentally from classical belt objects in their internal structure and surface chemistry, and whether the smaller bodies are truly primitive remnants or have been altered by processes we do not yet understand. 10 or 20 encounters would not be a comprehensive survey. The belt would still be overwhelmingly unexplored, but it would be enough to start building a framework, a statistical picture of what the Kuiper Belt actually is, rather than what we imagine it to be, based on 2 data points. That effort might take 50 to 100 years at current exploration rates. The belt is patient. It has been waiting 4.5 billion years. It can wait a few decades more for us to arrive. But here is the hard truth that no mission plan, no technological roadmap, no optimistic projection can escape. The Kuiper Belt is not a problem that will be solved by getting there faster. It is a problem of scale. Even if we could halve the travel time to every target, even if we could launch a mission every year, Even if every mission succeeded flawlessly, we would still be exploring a region that contains more worlds than we could visit in centuries. The belt is not merely far away, it is far away and enormous and diverse and almost entirely unknown. Getting there faster does not change the fact that there is vastly more belt than there is human capacity to explore it. Every spacecraft we have ever sent beyond Neptune has followed the same arc. Years of patient flight through emptiness. Hours of frantic data collection during a brief encounter, then silence, as the spacecraft recedes into deeper space with no ability to stop, no ability to return, and no second chance at the target it just passed. New Horizons spent 9.5 years reaching Pluto and collected close-range data for less than a day. It spent 3.5 more years reaching Arrokoth and again collected close-range data for hours. It has now been flying through the Kuiper Belt for over 20 years since launch, longer than many scientific careers, and is expected to exit the belt's main region by 2028 or 2029. When it crosses that boundary, it will have traversed only the inner portion of the belt. The scattered disk, the detached objects, the possible extended belt beyond 80 astronomical units, all of that will lie ahead and behind, unexplored, unvisited, unmeasured by any instrument at close range. New Horizons will keep going. It has no choice. Its trajectory carries it outward at roughly 14 kilometers per second, adding about 3 astronomical units of distance from the Sun every year. It cannot slow down. It cannot turn around. The belt will continue behind it, cold and silent, while the spacecraft pushes deeper into space that is even more empty and even less explored. Ahead of New Horizons lies nothing but the solar wind, the heliosphere's outer boundary, and eventually interstellar space. Behind it lies everything it was sent to study, receding at 31,000 miles per hour, getting farther away with every passing second. So what is the answer? How long does it take to reach the Kuiper Belt? If you mean the inner edge, where the population of frozen objects begins to thicken beyond Neptune's orbit at roughly 30 astronomical units, the answer is approximately 9 to 10 years at the speed of the fastest spacecraft ever launched, assuming a Jupiter gravity assist. Without the assist, add 3 to 5 more years. If you mean the heart of the classical belt, around 40 to 45 astronomical units where the densest concentration of objects orbits, the answer is 12 to 14 years at the same speed. This is how long it took New Horizons to reach Arrokoth. If you mean the outer edge of the main belt at 50 astronomical units, the answer is 15 to 16 years. New Horizons crossed that boundary roughly 15 years after launch, in 2021. If you mean the distant dwarf planets, the answer depends entirely on which one. Marquet, and Haumea could be reached in roughly 13 to 14 years. Eris at its current distance would take approximately 30 years. Sedna at perihelion would take over 23 years. Sedna at aphelion would take roughly 3 centuries. If you mean entering orbit around a Kuiper Belt object rather than flying past it, the answer changes category entirely. An orbiter mission to Pluto using electric propulsion would take approximately 75 years from launch to completion. An orbiter to Eris might take well over a century. An orbiter to any object in the scattered disk is beyond any mission architecture that currently exists on paper. These are not one answer, they are a spectrum. The Kuiper Belt does not have a single travel time because it is not a single place. It is a frontier extending from 3 billion miles to tens of billions of miles from Earth, populated by worlds that range from nearly Pluto-sized dwarf planets to house-sized fragments of primordial ice. The travel time to any point within it depends on which point, how fast, and why. But even these numbers, carefully broken down by target and mission type, fail to capture the deeper truth. The hard part is not that the Kuiper Belt is far away. Far away is a problem that speed can address, and speed is something engineers have been improving for decades. The distance to Pluto is large but finite. The time to cross it is long but measurable. Given sufficient priority and funding, we could send spacecraft to the belt every few years. The hard part is that reaching the belt barely constitutes exploring it. Our fastest spacecraft needed a decade to arrive and earned hours of observation before the target vanished behind it forever. Our most ambitious orbiter concepts require a human lifetime to execute. The belt itself contains more individual worlds than we could visit in centuries of dedicated effort. Reaching the Kuiper Belt is not the achievement we imagined it would be when we first asked how long it would take. It is the beginning of a confrontation with a scale that dwarfs our capacity to explore. The Kuiper Belt is a frontier in the oldest and most unforgiving sense of the word. It is a boundary between the known and the unknown, a place where human reach has exceeded human grasp by an almost absurd margin. We can touch it. We have touched it precisely twice. But those touches were momentary, lasting hours against a backdrop of decades, and they illuminated two tiny points in a wilderness that stretches billions of miles in every direction. The rest of the belt remains as it has been for 4.5 billion years. Frozen, dark, profoundly alone, holding its secrets in ice that no instrument has measured at close range, on surfaces that no camera has resolved, around worlds whose very existence we may not yet have discovered. New Horizons is out there right now, somewhere beyond 60 astronomical units from the Sun, still moving, still recording, still sending its faint radio signal back across a void so wide that each transmission takes more than 8 hours to reach the nearest antenna on Earth. Behind it, Pluto and Arrokoth have long since disappeared into the dark, their surfaces lit only by the distant pinprick of the Sun, their secrets partially revealed by a machine that spent hours in their company before leaving forever. Ahead of the spacecraft, there may be nothing, or there may be a third target, a small frozen body drifting in the blackness that ground-based telescopes might just barely manage to find before the spacecraft's path carries it irretrievably past. If they find one, New Horizons will photograph it during a flyby lasting hours. Then that world too will shrink behind the spacecraft, and New Horizons will continue outward, alone, carrying its data toward the boundary between the solar system and the stars. The belt stretches on behind it, cold, silent, overwhelmingly unexplored. Hundreds of thousands of frozen worlds, each one a time capsule from the birth of the solar system, each one carrying answers we do not yet know how to collect. We spent 20 years sending our fastest machine through the belt's inner region, and what we brought back was extraordinary, genuinely revelatory, and vanishingly small compared to what remains. 2 worlds seen up close, 2 brief windows of observation, 2 points of light resolved into real places with real geology and real histories. And then the belt closed behind us again, dark and silent, the same as it has been since before the Earth existed. The answer to how long it takes to reach the Kuiper Belt is not a single number. It is a spectrum ranging from 9 years to 3 centuries, depending on the target, the trajectory, and the mission type. But beneath those numbers lies a harder answer, one that the numbers alone cannot express. Reaching the Kuiper Belt is something we can do. We have done it. We will do it again. But reaching it is not the same as knowing it, and knowing it is not the same as understanding it. And understanding it would require a commitment of time, resources, and patience that no generation has yet been willing to make. The belt is reachable. It is not conquerable. It does not yield to a single mission or a single lifetime. It is too large, too diverse, too far, and too indifferent to our schedules and our ambitions. We reached the Kuiper Belt. We flew through it at 31,000 miles per hour. We photographed 2 of its worlds in detail that no one had imagined possible, and we changed our understanding of what the outer solar system contains. And then we kept going, because we had no way to stop, leaving the belt behind us, still frozen, still dark, still keeping most of its secrets locked in ice at the cold, distant edge of everything we have ever known.